Hello, this is MAT221. This is Mrs. Johnson. We are in section 4.1, which talks about applications to the derivative, in particular related rates. And in the last video, we saw this example having to do with the angle of rotation of the spotlight. And our answer was 16 radians per 125 seconds. Now we could reduce that if we wanted to. We could write it as a decimal approximation. And here was our answer. Again, this is from the worksheet from section 4.1 that you could find in Blackboard. This is example 4 of the worksheet, and it says, Tweety is resting in a birdhouse 24 feet off the ground using a 26-foot ladder, which he leans against the top of the pole. Holding the birdhouse, Sylvester the cat tries to steal the small yellow bird. Tweety's bodyguard, Hector the dog, starts pulling at the base of the ladder away from the pole at the rate of 2 feet per second. How fast is the ladder falling when the ladder is 10 feet above the ground? Again, these are difficult problems because of the fact that they're word problems and we have to set up the equation ourselves. So we have to decipher all of the information that's given to us in the problem. So if we look at this, the scenario is that there's a ladder leaning against a pole, which again looks like a triangular region. I know that the birdhouse is 24 feet off the ground. So I know this distance from the ground to the birdhouse is 24 feet. Now that's not going to change, but as the ladder slides down, as the dog pulls the ladder this way, right, the ladder is going to slide down this pole. So this length of this side of the triangle will change, even though the pole itself will always stay at 24 feet. I also know that the ladder is 26 feet long, and the ladder itself would be the hypotenuse of this triangle, and it also will never change because it's a given ladder that's 26 feet long. It's not going to get any longer or shorter, so that is not going to change. And we're also given that Hector the dog is pulling the base of the ladder, which is down here. He's pulling it away from the pole, so he's pulling it this way, away from the pole, at a rate of, so here's a rate of change. And remember, rates of change are derivatives, so we're given a derivative. We're given the derivative of the rate of change in this horizontal direction. And they're asking me, how fast is the ladder falling? Okay, so the ladder is going to be falling down the pole when the ladder is 10 feet above the ground. So when the top of the ladder is 10 feet above the ground. So the ground is down here. All right, so I circled all the information they gave us. Let's see if we can now look at this. We know the ladder is 26 foot long. And as it slides away, notice it's not going to change. It's still going to be 26 feet long, right? As we go along there. And it is moving this way. The dog, Hector, is pulling the ladder this direction. Now, I labeled this with a variable x because notice, I'll go back again. Notice that distance, the distance between the bottom of the pole and the bottom of the ladder is definitely changing. Correct? Now, what about the distance between the top of the pole and the bottom of the pole, or the top of the pole and the ground? As we pull the ladder away, that also is changing. So notice the only thing in the triangle that isn't changing is the length of the hypotenuse. It stays at 26 feet. So I know Hector is pulling that direction, and I'm going to call that x for a horizontal direction. And I know y is actually moving down here. I'm going to call it y because, again, it's a vertical direction. That also is changing. So notice I'm labeling those as both variables. So what do we know from the given information and these variables that we just put in here? And what do we need to find? Well, we know that the ladder's distance length does not change, so it's going to remain constant. The distance between the bottom of the ladder and the bottom of the pole, which is right here, this distance x, is increasing. And they gave us that it is increasing, that horizontal distance is increasing by 2 feet per second. Now the distance between the top of the ladder and the bottom of the pole is also changing. We called that y. And we can see that it is decreasing. Let's go back and look at that. We can see, right, that y is decreasing as x is increasing. So they're asking me, how fast is the ladder falling? In other words, here, what is the falling is this way, right? When y is 10 feet. So it's asking me, what's the distance between the top and what's the rate of change, of the horizontal or vertical distance here between the top of the ladder and the bottom of the pole. This is what we're asked to find. So again, with related rates, we know this is a related rates problem because we're given a rate of change and we want to relate them. What do we have to relate? In this case, we want to relate x and y. And again, if we look back at the 3 different types, usually we have, in this case, we have a triangle again. But there's no angle involved, so I won't use the trig ratios. I'll just use the Pythagorean theorem because I only want to relate the sides of the triangle and there is no angle involved in this case. So, how do we relate these rates? We could use the Pythagorean theorem. So we could relate these rates using the Pythagorean theorem. We know that x squared plus y squared will be equal to 26 squared. And I have information about x, I have information about y, and 26 stays constant. So I take the derivative of this expression implicitly. So I take the derivative with respect to time. Derivative of x squared with respect to time implicitly becomes 2x dx dt. The derivative of y squared implicitly with respect to time becomes 2y dy dt. And the derivative of a number, no matter what this is going to equal 0. Now, our goal was to find dy dt. So let's see what we have. We have a value for y at this time. Y is equal to 10 when the ladder is 10 feet above the ground. So y is 10. We have dx dt. We know that dx dt is moving at 2 feet per second. We said that was moving that way by 2 feet per second. So we have a value for y, we have a value for dx dt, and we want to solve for dy dt. That was our goal. How fast is the ladder falling? Well, we need a value for x there in order to complete this expression to solve for dy dt. So we should be able to figure it out from the information given. And if we look at this, if at this particular instant in time, y is equal to 10, then we could draw this little triangle and say, well, okay, y is equal to 10, the ladder is 26. What would the value of x be at that particular point in time? So at that particular point in time, I could use the Pythagorean theorem, x squared plus 10 squared equals 26 squared, and get x equals 24. So at this particular point in time, x is equal to 24. Now notice I had to do this little side work on the side to get this value in order to interpret and find the expression for how fast the ladder is falling. All right, so let's plug all these values in that we have. At this particular point in time, I know that x is equal to 24. I know dx dt is equal to 2 feet per second. I know y at this point, the ladder is 10 feet above the ground at this point, so that's 10. And I want to find dy dt. Okay, I have everything I need to actually solve for dy dt. So let's plug in and I get x is 24, dx dt is equal to 2 feet per second, y is equal to 10. Let's solve for dy dt. So I'm going to bring this becomes 2 times 24 times 2 is equal to negative 96 feet per second. And we're going to bring it to the other side here. Then I'm going to divide both sides by 20, and I got negative 4.8 feet per second. Now, why does it make sense to us that we got a negative number? Well, it actually does make sense because remember, when a derivative is negative, it means the quantity is decreasing. The function that it's coming from is decreasing, and you can tell that right here, y should be getting smaller. So I should have a negative number here for my derivative. All right, so at this point, I'm going to stop this video and I'm going to start a new one when we get to example 5, which will be quite more intensive. So hang on and look for our next video. Have a good day today.